And finally, we want to calculate the irradiance, not the electric field. We see the irradiance. And we know that the irradiance on the screen, if we have the electric field, we know we'll take the time average and take out the oscillating part, blah, 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 epsilon naught C E at P squared, 1/2 epsilon naught C E amplitude squared. So that means in our case, I will be 1/2 EL, the field amplitude per unit width, times the width over R. And I'm sorry, 1/2 epsilon naught C. Epsilon naught C times that squared, there we go, times sine beta over beta squared. And just like before, this is sort of the basic wave that's coming, and this is the diffraction pattern that you get on the screen. In fact, this, if you look at it, this is the field amplitude per unit width times the width. That's really the total field amplitude in the slit over R squared. This is basically the irradiance of what would get to the screen, of all the light in the slit. If it all just went to the screen, this is sort of like the total irradiance. This is basically I naught. If you take away the diffraction effects, this is the total radiance of the light in the slit. Okay, so we could call that I naught. We could say I equals I naught, and then this is actually a special function called sinc, the sine cardinal, right? So sinc of x is sine x over x. Or you can just think of it as sine x over x. But what we have here is a sinc squared. So I equals I naught sinc squared beta is the final shape of the function that we would predict. So if we plot that, it looks something like this. So here we're going to plot it as a function of beta, and we're going to plot the irradiance. So at 0, normally when beta is 0, so beta could be the angle up the screen. Normally when it's 0, sine of 0 is 0. When you have sine of 0 over 0, it goes to 1 in this case. You can apply L'Hopital's rule to see why. So you get a big peak like this, and it goes to 0 because the next 0 in the sine does not get canceled out, and then it oscillates like this. You get a peak coming up, and then it goes down again, and it's driven to 0 by the oscillations of the sine, and their amplitude goes down because it goes as 1 over x. So a sinc function actually goes plus and minus. What I'm plotting here is a sinc squared. Right, so remember, that's sinc squared. And beta is proportional to sine theta, so sine theta is going up and down around 0. So straight from the slit to here is the maximum, and then above the slit one way and below the slit the other way, we'll see these oscillations. That's the diffraction pattern through a slit. Now we can test it. So here is our source, a little chunk of a plane wave. That's our laser beam coming from over there somewhere. And I have a slit, and the slit's in, but it's big. I have it around, and it's not occluding the beam yet. So now I'm going to go, I'll be back, but I'm going to go and start closing the slit, and we'll see what happens. Let's see. So here it is, and I think this direction is closing it. And we'll start. Nothing happens. Oh, I'm opening it. Okay, now I'm going to close the slit down on the spot. Here we go. Now I'm closing the slit down on the beam spot. And eventually it'll start to spread it out. Let's see. Here we go. Now as the slit gets smaller and smaller, you see the beam is spreading because the light indeed is turning a corner. And you can even see it's making the pattern we predicted. So let me close it a little bit more and then come back and have a look. You can see a large central maximum here. That's the central maximum of the sinc function. And then it goes to 0 and comes back, 0 and comes back, 0 and comes back. Same thing here, 0 and comes back. And these modulations are the ones we saw when we did the Young's double slit experiment. These are the modulations that were modulating the fast oscillations due to Young's double slit. Here they're not spread out as much. I can spread them out by making the slit really small. So as I narrow the slit, they spread out even more, like that. So you can see that's closer to the oscillations we had when we were doing Young's double slit. So here's the central maximum of the sinc squared function. Here's the second. Here I think I can see the next peak. Okay, so that is single slit diffraction. And now I want to tell you two jokes about diffraction that I have. I told them every year that I taught this class on campus for 7 years, and no one laughed a single time. And I've never known if the jokes aren't funny or if the students didn't get it. It's one or the other. Now with the online audience, I have statistics, and what you can do is you can go post in the forum, was it not funny or did you not get it? And you can put it anonymous, because I don't want my feelings hurt, right? Okay, so two plane waves walk into a bar, and they say to the bartender, where should we sit? And the bartender says, sit by the sink. No, yeah, that's about the laughter I get when I tell it on campus. And then two photons walk into a bar. Photons say to the bartender, where should we sit? And the bartender says, sit by the square sink. Yeah. Okay, so let me know in the forum which of the two it is. Or maybe you laughed. Maybe you're the first one. I don't know.